Thank you very much. Thank you for having me. It's yeah, as you will see, I have not very much experience with in-person talks, so I haven't given many, but it's nice to be here and talk to real people and not just blank cameras. But right, so at any point, please feel free to interrupt me. Also, if you don't understand my handwriting, I try to do my best to write it, but just please stop me at any point. Okay. So I'm going to talk about Steklov eigenfunctions, and particularly going to talk about zero sets of Steklov eigenfunctions, and mainly I will focus on upper bounds on the Hausdorff measures, and hopefully you will know what all of those things are in the next few minutes. So let me dive into it. So the Steklov problem, which is this works. Okay, cool. So I'm talking about a bounded domain omega in Rd. And it will always be at least Lipschitz, which is already probably it's already too regular for most of you here. I apologize for that, but I will most of the time I will even be more regular than this. So again, apologies. It's the best I can do. Right. So the problem is about finding some real number lambda and u in the Hilbert-Sobolev space H1 of omega, which is just a harmonic function in the domain, and such that the normal derivative, so by d nu, I don't know, the normal derivative at the boundary is proportional to the function itself. And the constant of proportionality is this lambda, which we'll call a Steklov eigenvalue. This is sort of, it's not the most well-known spectral problem, but it's a spectral problem that is known. It's in particular, the spectrum is known. The first eigenvalue, which I'll call lambda 0, is 0, and the eigenfunctions are just constants, nothing to see there. And then there's a sequence of eigenvalues which accumulates to infinity. Okay, so it's a discrete spectrum. As an aside, I put here that you should at least under only Lipschitz regularity, you should maybe consider it as a weak problem. So the integral over omega of gradient 2 gradient v is equal to lambda integral over the boundary of uv for every v in h1 of omega. But it's not too important for the purpose of this talk. Right, so another sort of basic thing is that the eigenfunctions will be orthogonal on the boundary of the domain with respect to the L2 inner product. Okay, so a nice observation, which is sort of why people, I guess, maybe thought first about this problem, is that if you take this Steklov eigenfunction u, and you restrict it to the boundary, this is an eigenfunction of the Dirichlet-Neumann operator. The Dirichlet-Neumann operator, I guess you all know what it is I take a function on the boundary of a domain, I map it to its harmonic extension, and then I map that to the normal derivative. So it's the map that takes a function on the boundary to the normal derivative of its harmonic extension. So u restricted to the boundary is an eigenfunction of this operator. So a Steklov eigenfunction is the harmonic extension of an eigenfunction of the Dirichlet-Neumann operator. In particular, I'm interested in this talk in the zero set, which is just the set of zeros, as you may have guessed. So, and I'm interested in the interior zero set. So the point in omega such that u is 0. There's people in this area also study the boundaries of zero set. So the zero set of the actual eigenfunction of the Dirichlet-Neumann operator. So zeros on the boundary instead. Here I'll be studying interior zeros. So just to get a feel, how does this zero set look like? We can say very simple things at first, that if lambda is non-zero, then just by orthogonality of the eigenfunctions on the boundary, the zero set is non-empty. Another simple thing that we can say is that the maximum principle tells us that every component of the zero set has to intersect the boundary. Okay, I have here this omega, and the components of the zero set touch the boundary. Okay. Right. So let me give you just two ridiculously simple examples to sort of fix the ideas and what objects are we talking about. So my first example is I just take a ball, the unit ball in R2, and you take sort of the simplest harmonic function you can think of in R2, which I've written in polar coordinates as u of r theta is equal r to the k cosine of k theta. Okay. And the eigenvalue is just k. I've already draw near the sphere and the zero set, because otherwise it would take me 5 minutes just to draw this. But you can see how the zero set looks like. And in particular, what is the zero set is just lambda lines of approximately unit length. So the length of the zero set is approximately lambda in this case. And here and in the following, I will be thinking of lambda as being pretty large. So I'm interested mainly in asymptotic results. Okay, so this is the simplest example, I guess, of a Steklov eigenfunction I can think of. Another example, which is slightly less simple, but still very simple, is I take this time a rectangle in R2. I take a number alpha and I build this harmonic function u of xy, which is sine of alpha x hyperbolic cosine of alpha y. You can easily check this is a harmonic function, and you can check that this satisfies this the Steklov boundary condition. So the normal derivative is proportional to the function at the boundary, and the proportionality constant lambda, so the eigenvalue is alpha hyperbolic tangent of alpha, which the precise form doesn't matter too much. What matters is that lambda is approximately alpha. It's very close to alpha if alpha is large enough. One maybe interesting thing about this example that you didn't find in the sphere is that if there's sort of a difference between the sides of the rectangle you consider. So on the long sides of the rectangle, you have the zero set intersects and you have the expected number of intersections. Well, if you take those two sides of the rectangle, the sort of the short sides, you can see that there are no zeros at all. There's sort of a feature that, well, I thought I'll point it out, but it will not be the main focus of the talk. But it's caused by the fact that this boundary is not smooth, essentially, probably. But again, even in this case, for interior zero set, what you can, well, again, I drew the zero set, and you can see that, again, this is approximately lambda lines of unit length. So again, the length of the zero set is approximately lambda. So we've seen two examples in the plane, very easy, very simple. Two examples make a conjecture, and here I go with the conjecture. And the conjecture is sort of better motivated than this, and I will give a little bit of more motivation in a couple of minutes. But so the conjecture is that in general, if you take I have a domain, and let me be a bit informal about the regularity required on the domain for the conjecture. It can vary, but so this by this. Oops, sorry, I don't want to do this. This is the d-1 dimensional Hausdorff measure of the zero set, and the conjecture is that it's bounded above and below by a constant times lambda. All right, so it's essentially it's proportional to the eigenvalue. I will list some of the results about this conjecture, and I'll start with the sort of the strongest hypothesis in which we have the best result is that in 2 dimension for a real analytic boundary, which I indicate by C omega, then the conjecture is true. This was proved fairly recently by Poltorovich, Sharon Todd, 2015. If also in higher dimension, again with the real analytic boundary, the upper bound is also true. This was proved by Zhu in 2015. For only smooth boundary in any dimension, there's a polynomial upper bound, right? Then this was due by Giorgio van Roy-Fortan. I forgot to write the year. I believe this was 10-17. In terms of lower bound, as far as I'm aware, the best that we have is a result that I proved last year, which is in any dimension for a C2 boundary. I have a constant lower bound for the zero set. So the conjecture should have here a lambda. I don't know how to do that. It's that's the best I can do is with a constant. It's yeah. So before my result, sort of the bounds that we had were polynomially decaying in lambda. So at least I can show that that as lambda increases, the zero set does not decrease, but I cannot show that it actually increases so far. But the main focus of the talk will be actually on again a recent result for upper bounds, which I can say it in this way. So I'm taking a bounded domain, and I require the boundary to be C2. And actually, probably what I need is C11, but okay. Still too regular, I guess. Exactly. Right. What I can prove is I can get very close to the conjecturally sharp upper bound up to a log. So I can prove that the D-minus one-dimensional Hausdorff measure of the zero set is bounded by a constant that depends only on the domain times lambda log lambda. So I would like to get rid of this log, but I don't know how to do it. I would give actually I would say an almost fairly complete sketch of the proof if I manage to. But first, let me sort of give you a promise, I guess, in my abstract, a comparison with the Laplace eigenfunction case, which is maybe better known. I will digress a little bit on Laplace eigenfunction, which is it's a better studied problem, I would say. The classical setting is that of a smooth compact Riemannian manifold of dimension d. So this is a Riemannian metric. And the Laplace equation, the Laplace eigenvalue equation, and taking the Laplace operator with respect to this metric G, Laplace G phi lambda plus lambda phi lambda equals 0. And the sort of the guiding principle is that these eigenfunctions phi lambda corresponding to an eigenvalue lambda should look like a polynomial of degree approximately square root of lambda. Okay. Eigenfunctions look like polynomials, so the big conjecture of Yau is the sort of, you can think of it as a vast generalization, albeit less precise, of the fundamental theorem of algebra, if you will. So it says that the D-1 dimensional Hausdorff measure of the zero set should be bounded above and below by a constant times square root of lambda. So note that in the conjecture in the problem that I studied, the Steklov problem, I had lambda here, I have the square root of lambda. This is sort of the scaling of the equation. So the Steklov problem sort of scales like a first order problem. This is like a genuine second order problem. But okay, anyway, this is the right scale. The conjecture was formulated by Yau in the late 80s, and sort of close to the formulation of the conjecture, Donnelly and Pfefferman, in a very influential paper in 88, they proved it for a real analytic metric G. Okay, so when under very high regularity, real analyticity of the metric, the conjecture is true. And then, well, almost 30 years went by, and there were a lot of, progress in the middle that it will take me like all the rest of the talk to state, so I will not, and I will just state sort of a big breakthrough that happened in 2016 due to Sasha Logunov. He proved that when G is smooth, where smooth could mean C2, say, the lower bound is true in Yau's conjecture. And also in another paper, he proved that we have a polynomial upper bound. And we don't really know. This exponent in lambda depends on the dimension in not the nicest way. I should say, I guess, that before this polynomial upper bound, the previous bound was super exponential. So already the polynomial upper bound is kind of a big improvement. And yeah, it's especially nice that the lower bound is sharp. Okay. Even more recently, there was, you could ask, okay, here I talked about the setting of a smooth compact Riemannian manifold, so without boundary. What if you add a boundary, right? And this is a result that is even more recent. It's came out last year by Sasha Logunov, Eugenia Malinnikova, Nadirashvili, and Nazarov. They consider a bounded domain in RD. They consider the Laplace equation with Dirichlet boundary condition. And the domain it's a Euclidean domain. So in a sense, the metric inside is as real analytic as it could be, because this is just a Euclidean Laplacian. But the boundary of the domain is only assumed to be Lipschitz with a small Lipschitz constant. So the regularity is fairly low. And then they can prove this sort of the sharp version of the upper bound in Yau's conjecture for Dirichlet Laplace eigenfunctions. Okay, let me go back to Steklov, and I will remember what the problem. I will remind you what the problem is, just so that you don't forget it. So So the first thing I want to do is, it's a trick that I learned from a paper of Belova and Lin that came out in 2014, which is under high enough regularity sort of allows me to get rid of the boundary in a way and consider an elliptic equation in an open set. I'll briefly, and I will need this point of view. Let me explain what this is. So I take d of x, which is just the distance of x from the boundary, and say I'll consider this only close to the boundary and modify it in some way in the interior. It's not important really. Okay, then there's this nice trick. You define this function v of x, which is my Steklov eigenfunction u multiplied by e to the lambda d of x. What's the nice thing about this is that if you compute what equation v satisfies, you get v satisfies an elliptic equation with also lower order terms in the domain omega, but it satisfies a Neumann boundary condition on the boundary. So instead of this sort of weirder looking Robin type condition, Steklov type condition, we have a Neumann condition. When you have a Neumann condition, and if the boundary is sufficiently nice, you can do sort of an even reflection across the boundary, right? You can map sort of this part into this part and define the function across the boundary. If you do this, you get a sufficiently nice elliptic PDE in an open set where I'm talking about Lipschitz second order coefficients, uniformly elliptic with sort of unbounded lower order coefficients with a bound that I can calculate in terms of the eigenvalue. The precise form is not that important. What's important is that the boundary sort of disappeared in this formulation. And for the rest of the talk, I will need to keep these 2 points of view in mind. So I'm both viewing a Steklov eigenfunction as a solution of this thing, with these bounds on the condition, and also as my original problem with an actually Euclidean harmonic functions, but with this boundary condition. I will sort of keep these 2 points of view in mind because I will need to switch back and forth morally. Okay, right. So Eugenia last week in our course talked extensively about frequency functions and doubling indices, and these of course play a role in the proofs of this type of things. So let me define what I'm talking about. Particularly, I'm defining a doubling index, which shall have a star there, and the star is for the boundary. So this is a doubling index at the boundary. I'm taking the sup over a ball centered at x, radius 2r, intersect omega, divided by the sup over half the ball, intersect omega. So this is a version of the doubling index that takes into account the boundary. So here I'm just reminding you what the usual doubling index is for sort of my extension across the boundary function which doesn't see the boundary. And if I'm sufficiently close to the boundary, so at the distance no more than 1 over lambda, and also if the radius of those balls is less than 1 over lambda, then these two quantities are comparable, which is one of the reasons why I need this extension. Okay. I also defined like a maximal version of doubling indexes, but for cubes, for reasons. So this is just the sup essentially of the doubling indexes over balls where the diameter of the balls is less, when the radius of the balls is less than the diameter of the cube. Okay. And yeah, I allow points on the boundary as well. Okay. So there's a useful theorem that by Zhu in 2015, which tells me that if I take this doubling index in half balls around the boundary, then this is bounded by a constant times lambda. The proof of this uses Karleman inequalities, and it sort of mirrors the proof of Donnelly and Pfefferman for Laplace eigenfunction, which gives you that this is less than a constant times square root of lambda, but as we know, the scaling is what it is. So the proof uses Karleman inequalities, and it would be nice to have a proof, a sort of a frequency function proof. So for Laplace eigenfunction, there is a frequency function proof of the doubling index bound. For Steklov eigenfunctions, I don't know how to do it. It should be possible, but I don't know how to do it. Okay, so let me really dive sort of into the scheme of the proof now. And I need to remind you, as you probably all know better than me, but what a Whitney cube is in this context is just a cube such that its side length is comparable to its distance from the boundary. And in this notation, I can sort of reformulate the big result of Donnelly-Pfefferman, which says that if I have any Whitney cube, then the Hausdorff measure, the d-1 dimensional Hausdorff measure of the nodal set of U inside this cube is bounded by a constant times the doubling index in the cube plus 1 times the side length of the cube to the d-1. Okay. And so U was my harmonic function, and here I really need U to be harmonic, where this is the Euclidean Laplacian, or at least I would need a real analytic metric, but let's say Euclidean Laplacian. So I will apply this this estimate of Donnelly-Pfefferman many times in my proof, and this is sort of where I need the point of view that when I'm inside the domain, I actually have a Euclidean harmonic function, because we don't know that this result is true for more general PDEs. This is sort of the key thing missing from a genuine proof of the upper bound in Yau's conjecture for more general elliptic equations, right? So we only know it for the Euclidean Laplacian. So what I'm going to do to apply this this bound of Donnelly-Pfefferman, I decompose my domain into an inner part, which is as a fixed distance from the boundary, a middle part where I'm going from a fixed distance to the boundary to a distance which is like constant over lambda, and then a boundary part, which is the points which are at the distance from the boundary less than constant over lambda. You can already guess from this estimate of Donnelly-Pfefferman that I can take care of the inner part of the domain without any difficulty. I can say immediately that the zero set intersect in the inner part as Hausdorff measure less than lambda. What I do in the middle part is I do a Whitney cube decomposition. So I go from distance C0 to the boundary. This is C0. This is C0 over lambda. And I do it in about log lambda steps. And I apply this inequality of Donnelly-Pfefferman at every step. And this gives me that I can bound the portion of the zero set in the middle part by lambda log lambda. So here I lose a lambda. I lose a log lambda because I need log lambda steps to get to distance C0 over lambda. But I need to get to. So the thing is, I only understand Steklov eigenfunctions at distance constant over lambda from the boundary. When I'm further away, the best I can do is just apply Donnelly and Pfefferman, and just I have a harmonic function with bounded doubling index, and that's the most I can say. Okay. So the last thing I need to do is I need to estimate the zero set in the boundary part, which was this last part of my decomposition. Okay. So I'm at distance constant over lambda from the boundary. What I do is I cover this boundary with cubes, which are, say, approximately lambda to the d-1, cubes q lambda. The side length of these cubes is constant over lambda. And I just focus on one of them, okay? And the goal is to get an estimate of the portion of the zero set in this cube, which is linear in the frequency. Okay, where n is say the doubling index in a little enlargement of the cube. Doesn't matter how large it is. Okay, let me just rescale the problem because I think it's a bit more clear. So I take one of these cubes, I bring it to unit scale. So the problem I'm left with is I'm trying to study harmonic function in, say, an enlargement of the cube with its normal derivative, which is equal to the function on the portion of the boundary inside the cube. And maybe I should call this omega tilde because sort of, yeah, I rescale this so the domain has changed, but it has only gotten better. So it's not too important. And the estimate that I want to get is, again, I want to say that the d-1 Hausdorff measure of the zero set of H in this cube is bounded by a constant times the doubling plus 1. Okay. The main tool to do this is a version of the hyperplane lemma of Sasha-Logunov. A sort of a closer version of this appears in the paper I mentioned before of Logunov, Malinnikov, Nadirashvili, Nazarov. So this is not really a hyperplane lemma, it's sort of an hyperboundary lemma. So I have a curved portion of the boundary. And I need to prove it also for, so in this paper, they have it for essentially harmonic functions which are 0 on a portion of the boundary. I have this sort of weirder condition that I need to prove it with, but it's not too bad. So what this lemma says is if I cover the portion of the boundary inside my cube by 2 to the k d minus 1 cubes qj, so of side length 2 to the minus k. Sorry, this is not very visible. Okay, where k is a constant that is much larger than 1, but independent of the doubling index. If my doubling index is large enough, then there is one of these subcubes which is doubling index which is less than n over half. So my doubling index drops in at least one of the cubes. The proof of this uses quantitative Cauchy uniqueness. Okay, this is the main thing, the main ingredient that goes into it. So I want to use this hyperplane lemma, and I'm almost done, luckily, because I'm almost out of time. I define this quantity, this function a of n, which is the sup of the Hausdorff dimension of the Hausdorff measure of the 0 set of h inside a cube q divided by the side length of the cube to the d minus 1. This is just scaling. What's the sup over? The sup is taken over all harmonic functions in, say, 10 times the cube, which with this condition on the normal derivative on the boundary intersected the cube, and all cubes contained, all subcubes q contained in my large cube q. And I assume that the n comes from the bound on the doubling index on, say, on enlargement of the original cube. So first of all, this is an important point. A priori, there's no guarantee that this a of n is finite, right? It's this is guaranteed by a result of Hard and Simon in '89. And this is one of the key places where I need to use this extension across the boundary. Because this result of Hard and Simon applies to more general elliptic PDEs, and it gives me a bound on a of n, which is quantitative in n. It's bad, it's like super exponential, but it is something. And I sort of use it as a starting point in an induction argument. Okay. So I know this is finite, and in particular, if I know that my doubling index is, say, uniformly bounded, I'm already done. Okay, there's nothing to do. So I assume that n is large enough, and I want the recursive inequality for a of n. And I didn't finish my slides now. I'm joking. I left something for myself to do to write at the end. So I'm going to start with writing the Hausdorff measure of the 0 set of my harmonic function h inside this cube, and I can bound it by a constant that depends on k times n, and this is Donnelly-Pfefferman. Essentially, let me show you again. So I have here my boundary cubes, and the rest of the portion here I can bound it just by Donnelly-Pfefferman. Then the hyperplane lemma gives me that I have one. Oops, maybe I should write in. Yes, black is better. I have one special cube, which I'm going to call Q0, which has lower doubling index. And then I have all of the other cubes. How many I have? I have 2 to the k d minus 1 minus 1. And then I have the portion of the 0 set inside these cubes. Okay. Here I just applied the definition of an. So that's why I took these sups over all these cubes, because then I can use it here. So I keep this ckn. And then here, what do I have? I have a, but in the frequency n half, because this was the special cube given by the hyperplane lemma. Okay. And then I have to scale by the side length of the cube. Sorry, actually not by the side length, but yeah, side length to the d-1. And here, okay, here I don't know better. I don't know anything better about the doubling index. I know that it's just bounded by, a to the n, the right scaling. And again, I have to rescale. Okay, I pass to the soup also on this side, and what I get is that an is less than ckn plus a n of. I iterate this many times, and I get that this is bounded by ckn until I get to a n0, where n0 is some phase constant, and this is less than ck times n plus 1. This is what I wanted. If I go back to the definition of an, I proved that an is bounded linearly in terms of the frequency, in terms of the doubling n. This is so this is the end of my proof, and also the end of my talk, because I'm out of time. And thank you very much for bearing with me at this hour.